Awesome. Thank you so much for being with us today. I'm very glad to have Andrea with us. Andrea is a PhD student with focus on quantum machine learning. Her research interests include quantum machine learning algorithms for near-term quantum devices and how quantum computers can be used to solve learning tasks in supervised, unsupervised, and reinforcement learning. Before starting her PhD, Andrea received a master's degree in computer science with a focus on machine learning and worked as a software developer to solve machine learning tasks in industry, amongst others. So I'm very glad to have you here with us, Andrea, today, and I'm very excited to hear about your work.
Thank you.
Of course. So just to give a bit of intro about your work, so essentially, you are looking into near-term quantum devices that are more realistic. And one of the problems that people have pointed out previously is that when you try to do the quantum version of neural networks on these systems, when you're calculating the gradient to train these models, the gradient vanishes at some point. And people have shown that this is because of the size of the device, essentially. Like if you increase the number of qubits because of the hardware noise and other things that exist, it becomes difficult to read the gradient at some point, and it just gets to a plateau. And in your work, you come up with a way to get around that problem, which is quite interesting. And we get into more details about that shortly. So, but before getting to the details of the work, I would love if you could go through some of the concepts that you use in the paper so that everyone is familiar with those essentially keywords as we go through. So the first thing is, I know there are a bunch of other things like quantum bits and quantum gates, et cetera, that you have in your presentation. So I'm not going to go through those. But one of the things that you talked about is barren plateaus, and that's essentially the problem that you're trying to solve here. Can you give us a very quick overview of what that is?
Yeah, so fundamentally there is this problem when training quantum circuits, which I will explain later what exactly that means, that as we increase the number of qubits and the number of layers in the circuit, the variance of the gradients we want to compute will vanish as a function of the number of qubits and the number of layers. And this is a problem in general, even for fault-tolerant quantum devices, but is more severe on near-term devices where we also have to tackle readout error and hardware noise.
Right, very interesting. And you're talking about the general context of quantum circuits, but specifically you're looking into random quantum circuits. Can you tell us what that means?
Exactly. So this phenomenon of barren plateaus has been formally introduced in the context of random circuits, where so I need a bit to explain a bit more what a quantum circuit is, but basically you can imagine like if we would choose in a classical neural network the activation functions and the general configuration of the neural network in a totally random way, and also the initial parameters.
Right. And in a paper, you know, in the title of your paper, you're talking about a layer-wise training. And when I see layer-wise and neural networks in the same sentence, I just imagine the layers of neural networks. But I believe that that's not what you mean. Can you elaborate on that a bit?
Yeah, so in a quantum neural network, you also have layers, but different than classical neural networks, these layers, so the gradients of individual layers are not computed by using the chain rule and then backpropagating, but we always have like one contiguous circuit that we then calculate partial derivatives of the individual parameters. But the circuit itself is still made up of layers.
Very cool. And there are two kinds of learning that you're comparing here. One you call layer-wise learning, which is what you will go into depth about it in your presentation. But you also talk about complete depth learning. Can you just quickly compare what you mean by these two?
Yeah, so complete depth learning is basically the standard way to train a quantum circuit. So you have one quantum circuit and its parameters, and then you update all parameters in one step. And in Layerwise learning, you only update certain sets of parameters at one time.
Very interesting. And you specifically talked about NISQ devices, NISQ, noisy intermediate scale quantum devices. Can you also tell us what that means?
Yeah, so most famous quantum algorithms like Shor's algorithm are made for so-called fault-tolerant quantum devices, which have no errors at all. But the devices that we currently have, for example, Google's and IBM's devices, they still have a low number of qubits, like around 50, and also no error correction at all. So they still suffer from hardware noise.
Okay, so essentially by NISQ devices, you mean the realistic devices that we have rather than the ideal devices that we will have in some unknown future.
Yeah, so in general, we call NISQ devices those which we expect to be there in the next 5 to 10 years.
Okay, right. And you mentioned in the paper, that was something that I didn't know, that quantum neural networks is a special case of parameterized quantum circuits, or PQC. Can you elaborate on that a little?
Yeah, so in general, basically all quantum algorithms are a parameterized quantum circuit, if you look at it from a formal way. And what we call a quantum neural network is really a circuit that you train on its parameters by a set of samples, like you would in a classical neural network. And for example, other ways to train parameterized circuits could be for just optimization. So you don't have a data set, but you have an optimization problem that you encode into your circuit and then optimize for this, which is not a quantum neural network. So basically, the name quantum neural network just refers to something that is trained on a set of data.
I see. So I guess I'm a little confused here. So quantum circuits are in general parameterized. So just saying parameterized quantum circuits doesn't mean any special kind of quantum circuit, right?
So parameterized somehow implies that you optimize the parameters, but you can also have non-parameterized circuits, which are basically just sequences of quantum operations, which is a quantum algorithm.
Okay, interesting. All right, and in your paper, you're not using a real quantum computer. You're using a simulated quantum computer.
Right.
Can you explain what is happening there?
Yeah, so basically, as we don't have unlimited access to quantum devices right now, even though some of them already exist, we use simulators to verify our theoretical work. So what we do is in our work specifically, we use Google's Cirq library and simulate quantum circuits with that.
I see. And is that part of TensorFlow Quantum, or is that something different?
Yeah, so TensorFlow Quantum basically combines TensorFlow and Cirq so that you can optimize by using the classical optimization tools in TensorFlow. You can optimize quantum circuits.
Very cool. All right, that's all the questions that I had to essentially warm it up. Now I hope that people are ready for your presentation. So let's go into that.
Okay, thank you. So let's start. Yeah, basically, I'm going to give you a very, very brief introduction to quantum computing and what quantum neural networks are, how we encode the data, and how we compute gradients. Then I'm going to explain why we also get vanishing gradients in QNNs, even though we don't really do backpropagation in that sense. And of course, I'm going to explain our method to tackle that problem, which is Layerwise learning. Yeah, so first, what is a quantum computer? So unlike classical computers, which work with bits, a quantum computer uses quantum mechanical effects to perform computations. Most importantly, these effects are superposition and entanglement, and superposition is what people like to call being in multiple states at the same time, but mathematically, this is basically just a linear combination of classical bit strings. And then we have entanglement, which is correlations over multiple qubits, which you cannot represent just by considering the subsets of qubits. So basically, we store information in correlations between qubits. Now, these effects give rise to the state space in which our quantum computer operates, and the state space grows exponentially in the number of qubits. So whenever we add a qubit, the space grows exponentially. So this means that if you want to simulate 48 qubits exactly, you would already need a state-of-the-art supercomputer. And if you want to simulate 300 qubits, you would need an amount of bits that corresponds to the number of atoms in the universe. So this is basically impossible already at 300 qubits. Now, if you don't want to do it exactly, it's a different story, but that's out of the scope here. Okay, so now let's look at what a qubit is mathematically. So can you see my cursor, by the way?
Yes.
Yes.
Great. So here we have this state psi, which is our qubit, and this is a linear combination of the states 0 and 1 multiplied by the so-called amplitudes alpha and beta. And these amplitudes are complex values, which we multiply with the state vectors. So this here is the state vector for the state 0, and this is the state vector for the state 1. And these amplitudes give us the probabilities with which we would measure the qubit in state 0 or in state 1. That's why they have to also, the absolute squares of these amplitudes have to sum to 1. Another way to look at a qubit, which is maybe a bit more intuitive, is this Bloch sphere. So here, basically, the state of the qubit is represented as a point on a unit sphere. And now this point is given by the angles theta and phi. And here you see this yellow dot represents now our quantum state. And at the north pole of the sphere, we have the state 0, and at the south pole of the sphere we have the state 1. And now if we want to get information out of a qubit, we have to make a so-called measurement. And this means that we have to decide first in which basis we want to measure. So in general, we measure in the Z basis, which we call just the measurement in the computational basis. And then we project the qubit, so the state, onto this basis. And here we now get probabilistically states 0 and 1, where the probability is given by the amplitudes that I showed you before, this alpha and beta. So in this case, if we look at this black dot, which is now our state psi, with higher probability, this would be projected onto the 0 state. But it could still happen, if the probability is not 0, that we would measure the state 1 in the end. So what is very important to keep in mind when we talk about quantum computers is that all the outputs that we have are just probabilistic measurements of the quantum system, and every output has to be averaged over multiple measurements of the system to get a good picture of the output that we're measuring. Okay, so now what is this quantum circuit that we have talked about before? So basically, the sphere that I just showed you is a nice way to visualize one qubit, but of course you want to work with more than one qubit. And for this, we visualize these operations in so-called quantum circuits, which you can intuitively imagine like assembly language for quantum computers, basically. So we manipulate qubits directly, so we don't have a high-level computer programming language like you would have in classical computing. So here we have the qubit lines. So we have one line per qubit. In this case, we have 4 qubits, and we read the circuit from left to right. Then these rectangular boxes are called gates, and they basically perform operations on qubits. And in this case, we have rotations around the x, y, and z angles. So in this case here, the parameter of the rotation is 0, so these gates wouldn't actually do something. But here where the zeros are would be, in general, the rotation angle that we use for this gate. And then we already have these vertical lines here, which are so-called controlled gates, and these are used to create entanglement between qubits. So now we build a quantum neural network basically out of these quantum circuits, and it looks like this. So in this case, we first have to encode our data. Of course, if we want to learn on a classical data set, we have to somehow encode this data set into something that the quantum computer can understand, which means it has to be a quantum state. There are several ways how to do this. I will introduce one of them, I think, in the next slide. So step 1 is encoding the data, which is here in yellow. Then step 2 is now the parameterized quantum circuit part of the QNN. Basically, again, we have some parameterized gates now, and what we learn in this QNN is the angles of the individual rotation gates. And the controlled gates that we use here are fixed. And then, of course, we also want to compute the output from the QNN, which is here marked in green. So in this case, we are measuring the third qubit. And also here, we take a number of measurements to estimate one output from the circuit. This we then compare to the data labels, just like you would do in the classical neural network, and compute the loss function derivative to update our parameters. So basically everything that's colored here in orange, blue, and green would run on the quantum device, and then you would have an outer loop optimizer on a classical computer. Okay, so the first step is to encode our data. Like I said, there are a number of different ways to do this. This is one of them, which we call qubit encoding. And so basically on this example of an MNIST digit, so this has 28 by 28 pixels, which would mean we would need over 700 qubits if you want to directly encode each pixel, which we don't have right now. So what we do is first we have to downsample the image to something that is simulatable or fits on the quantum device, depending on what we do. So we do this, we flatten this vector, and then we have a vector of values. And if you want to use these values as rotation angles, we will also scale them to lie between 0 and 2 pi. Now basically 2 pi is the full rotation. And then we take this vector, which I call d here, and we use the now angles in this vector to generate these rotation angles in the circuit. In this case, we encode our data into rotations around the x-axis of the qubits. Okay, then how do we read out gradients? So this looks a bit more scary than it actually is. So basically, there are two main ways that people compute gradients in quantum circuits. The first is just finite differences, which you probably all know. So basically, you can compute for any function that's differentiable by this finite difference method its derivative by the parameter, in this case, theta I. And of course, you can also do this with a quantum circuit. So here, this first part is the expectation value of the quantum circuit with the parameter theta I shifted by epsilon. Then you subtract the expectation value of the unshifted circuit and divide the whole thing by epsilon. This gives you an estimation of the gradient with precision epsilon. Then the second way is called the parameter shift rule, which is something unique to quantum circuits. So basically with this rule, which looks very similar to the finite differences, but is unrelated to this, because here this is just the actual analytical gradient of this quantum circuit. And to compute this parameter shift gradient, we have to execute again first our circuit, this time shifted by pi half plus, and then again by pi half minus on the circuit parameters. And by computing this difference and multiplying with this factor, we compute the exact gradient of the quantum circuit. But the downside is that here we have to compute 2 expectation values per parameter, while in the case of finite differences, you have to compute 1 expectation value per parameter plus the unshifted expectation value. So that's the downside of the parameter rule. Yeah, so so the main difference also when we compute gradients in quantum neural networks compared to classical neural networks is that we don't really do backpropagation. So we don't have layers and then repeatedly apply the chain rule to compute gradients of these layers, but we always have one contiguous circuit, and then we compute partial derivatives depending on the parameters. But it turns out that we still have vanishing gradients in these QNNs. Let's now look at why this is the case. So, because the reason for these vanishing gradients is so different than the classical reason, the community also came up with a different name. So we call these types of vanishing gradients barren plateaus in QNN training landscapes, and they have first been formally introduced in this paper that I wrote here below by Google. And basically, they showed in the context of random circuits that the gradients vanish as a function of the number of qubits and the layers in a circuit. So first, we have to define what a random circuit is. So now if I go back to this guy, a random circuit would be a circuit where you choose the gate. So you choose the rotation axis, Z, X, or Y, and the rotation angle randomly for some fixed configuration of controlled entangling gates. So they have shown that for these types of random circuits, as you increase the number of qubits and layers in your circuit, the variance of the gradients vanishes exponentially. Here you see in this figure the variance of gradients from 2 to 18 qubits and from 1 to 200 layers. And here, another thing that plays a role is the cost function. So if you use a local or global cost function, where global cost functions run into plateaus earlier, and also the connectivity of the circuit is important, where basically a circuit where all qubits talk to all other qubits will exhibit this barren plateau issue the fastest. Okay, so, and this problem is like a fundamental issue in computing gradients of quantum circuits, no matter of the device you are on. But if you use these NISQ devices that we talked about before, you will also have another problem, because with NISQ devices, you also have errors, so your readouts are not very exact. And the deeper your circuit gets, the more noise on the hardware level will hit you. So this is a problem. So the quality of our gradients is really limited by how large the partial derivatives are. Because also remember that we have to take multiple numbers of measurements to estimate one expectation value. So the smaller the value that you want to estimate, the more measurements you will need to do a good estimate. And if our gradients are so small that they cannot be distinguished from hardware noise anymore, we're just totally lost. Okay, so if you want to avoid barren plateaus, we need to first not initialize on a plateau, obviously, but also we need to prevent the circuit from entering a plateau while we train, for example, when we approach a local minimum. Okay, so then the method we developed for this is called Layerwise learning, and here we use the fact that shallower circuits produce larger gradients, like in this figure. Here you see that the fewer layers in one circuit, the larger the gradient variance is. So we use this, and also to avoid initializing on the plateau, we build the circuit at runtime. So we initialize with a very shallow circuit and then go from there and build it during training. And once we have finished this first step, we also have a good starting point to optimize over larger partitions of the circuit. So we avoid the initialization on a plateau, and we also prevent entering a plateau during training. Okay, so to take a closer look at how we do this, basically the algorithm works in two phases. And in phase one, we start with a very shallow circuit, which could have 1 or 2 layers, very few, and we optimize the parameters in this layer until a fixed number of epochs. Then we add another set of layers and freeze the parameters of the previous set of layers, and in this step we only optimize the second layer's parameters for a fixed number of epochs. And here in this graph, the blue rectangles are layers with parameters that are optimized, and the gray rectangles are layers with parameters that are frozen. So we go on. In the next step, we add a third layer, freeze the previous layer, and optimize only the parameters in the third layer, and so on, until we reach predefined depth. Okay, then we use this circuit as a starting point to now optimize larger contiguous partitions in the circuit. So now we divide the circuit again into larger partitions, for example, in halves or quarters, and then optimize only the parameters in that partition. And we sweep sequentially over these partitions of the circuit, and we do this until the algorithm converges in loss. And here you basically have a trade-off between how big or small you make these layers. So if you make them too small, your learning progress will be very slow because you always update very few parameters in one go. But if you make it too large, you will also run into the spiral plateau issue here, because what has also been shown in the original spiral plateau paper, as soon as one part of the circuit enters the spiral plateau, the whole circuit will be susceptible to the spiral plateau phenomenon. So you have to take care to not choose your partitions to be too large. And basically what we want to do in phase 2 is to decrease further the loss, and we don't optimize all parameters here in one go, because if you imagine your loss descending and the gradients getting smaller, and you always optimize all parameters in one step, it could happen that due to the hardware noise, you would get a wrong parameter update, which immediately affects all of your parameters. So the circuit could enter a random configuration during runtime and then not escape from there anymore. So by only updating subsets of parameters, we contain these randomization effects in smaller parts of the circuit. Okay, so in the paper, we have looked at an example for NISQ classification to show how our method works. So basically what we do is we train a circuit to distinguish between the numbers 6 and 9. And we compare to complete depth learning, which is just the standard training scheme that is used. Basically, we update in each step every parameter of the circuit. And because we wanted to directly compare to the original Barron Plateau paper, we used the same structure for our layers as stated. So we used the random quantum circuits, where one layer consists of one local gate on each qubit, where the rotation axis is chosen randomly, so x, y, or z, but the rotation angle is initialized with 0. And we use all-to-all connectivity in our circuit, just because this is like the worst case scenario where the Barron Plateau phenomenon will hit you with the smallest number of qubits in layers, which was also convenient for our simulations, because then we could look at smaller systems and still look at something that's hard. And we look into measurement noise here. So basically, remember that if we want to estimate an output from the quantum computer, we always have to take numerous measurements. And here we take a very small number of measurements to really make apparent this effect of the size of the gradients, because if you want to estimate a smaller value, you have to take more measurements to get an accurate estimate. And we here set the number of measurements to just 10 for each expectation value. Okay, and here are some results. Here on the left, you see the success probability of the different methods as we demand a higher and higher accuracy. So the orange and blue curves is layer-wise learning, and the red, green, purple, and brown is the complete depth learning. And here you see that for the CDL, the success probability decreases almost linearly, while for the layer-wise learning, in the beginning it's constant and then just starts dropping as the accuracy has to get higher than 0.65. And on the right, you see the same training runs, but now plotted with respect to the estimated minutes we would need to run on an actual quantum device if we assume a sampling rate of 10 kilohertz. And here you see that not only does the test error go down lower than for the complete depth learning, but it also goes lower faster. And this is also due to the lower number of parameters we train overall. And what's also interesting to see here is that for the CDL, some of them seem to get a higher test error as they progress in training. This might look like overfitting at first, but here it's important to note that these runs are averaged over 100 individual trained circuits. So what's really increasing here is not the test error in general, but it's the number of circuits that have randomized during training. So at first they go down just fine, but then as we progress in training, a larger number of circuits just enters the plateau while it trains. And also notably here, the circuit, the red one that did best in this success probability picture is also the one that takes pretty long to train compared to, for example, the purple and brown curves. So here we also compared different learning rates because intuitively you could also say, okay, we can contain these randomization effects just by setting a smaller learning rate, then you wouldn't immediately get lost by a bad parameter update. But it turns out that you would have to set extremely small learning rates that just blows up your training time if you want to avoid this effect. And even at these relatively small learning rates, in the end, it's not that helpful. Yeah, so that's basically it. If you want a deeper dive into these topics, please check out these additional resources. So we have also a blog post on the TensorFlow blog and a notebook with some code in TensorFlow Quantum if you want to play with this yourself.
Thank you so much, Andrea.
Thank you.
So I have a bunch of questions for you that we can go through them one by one. So maybe just to quickly summarize, if you can, briefly tell us. I mean, I know you went into a lot of depth about it, but just quickly summarize what is the main claim here.
So the main claim is basically that with layer-wise learning, you can reach on this device where we only look at measurement noise, you can reach a lower test error with smaller runtime because of the larger gradients in shallow circuits.
Okay. So, and the intuition for it is that if you try to train the whole circuit in one go, what happens is that the system just gets into hardware noise or other types of noise and just gets confused and can't make progress beyond a certain point.
Yeah, because as you decrease the gradient values, for example, when you enter local minima, then the gradients get smaller and smaller, and you could have parameter updates which lead you into a more random configuration. And once you enter this, the circuit cannot escape from there anymore. Okay,
makes sense. And obviously, the work that you've done is a simulation of a real quantum computer. So what would you say is the most fundamental / riskiest assumption that your simulation is making that might, break the results of your work?
So here, the most fundamental is that we only considered measurement noise. So the measurement noise occurs at the end of the quantum computation. So the circuit depth itself doesn't really affect the measurement noise. But what you also have on a real device is, of course, hardware noise that occurs during the computation. And here, this will get really worse as your circuit goes deeper and deeper. So here we have not considered that because it's very computationally intensive to simulate. So, and also, if you look at this picture, so in the first step, the circuits grow larger and larger during the optimization. So it could still get away even with the hardware noise, but in the second step, the hardware noise would also affect us.
Right. While we are on this slide, I had a question. Like I'm trying to test my understanding. So essentially, you divide up your circuit into, say, let's assume n is 10 for sake of argument. So let's say you divide it into 10 pieces, and you start training one by one, and then freeze the previous one until you reach the end of it. And then I didn't understand what you do in step 2. In step 2, you just merge, say, every 2 pieces together and repeat what you did in step 1. Is that what's happening?
Yeah, so if we have, let's say now 10 layers, and in step 1, we only ever train 1 layer at a time. And then in step 2, we say, okay, now we're ready to train larger partitions. So for example, we train layer 1 and 5 together, and then we train layer 5 to 10, and we alternate between these 2 until we converge.
I see. And what is the reason for alternation?
So basically, you don't want to train all the parameters at once, right? So you first pick one subset where you train the parameters, and then you go over these subsets, and this prevents the circuit from being affected in all parameters by like one wrong parameter update. So if something bad happens during optimization, it's contained in one subset of the parameters.
I see. Very cool. And essentially, I guess the point of repetition here is that it's not going to converge to the result that you want after one go, so you have to just iterate until it converges to the solution you want.
Right, yeah.
Okay. And again, like that brings up another question that I wrote down to ask, which is, you mentioned that if even a small part of this circuit falls onto the plateau, then the whole circuit is gone, kind of, which sounds a little too dramatic. Like, what is the intuition there? Like, why does that happen?
Yeah, so basically, it's just a mathematical property of how these barren plateaus work. So basically, you can show that if one part of the circuit suffers from this barren plateau phenomenon, then the whole circuit suffers from this. So it sounds a bit too dramatic, but yeah.
Is there some sort of physical intuition why that happens?
I'm not sure about physical intuition, so it's just a mathematical property of how you compute these derivatives.
Okay. Yeah. And I guess another question that I have is, when I wrote down the question, I hadn't appreciated the fact that quantum neural networks and classical neural networks are very different in terms of how they behave. But in the past, we've seen many cases where, progress on quantum, replications of machine learning provides insight that we can take back to classical machine learning. Is there anything like that came to mind as you were doing this research?
I'm not really sure. So this barren plateau phenomenon and why it's there's very specific to quantum circuits. But I mean, there has been some layerwise learning in the 90s, 2000s. I'm not sure anymore when. But layerwise learning also has been used for classical neural networks as a pre-training scheme to find good initializations also for vanishing gradients in classical neural networks. But then people found other methods like clever initialization or different activation functions. So I guess here it's not really needed anymore.
Okay. And is that how you got your inspiration to try this, or was the inspiration from somewhere else?
No, the inspiration was mainly that, okay, if we cannot train the whole circuit at once because larger numbers of layers will put us in a plateau, then what can we do to not initialize and run into a plateau? Can we split this up somehow in smaller parts and then train these? That's the basic inspiration.
So essentially the fact that one of the observations from one of the previous works was that the fact that the circuit becomes bigger is the reason that you're falling on the plateau inspired you to try to see if you can do smaller trainings one at a time and then combine the whole thing.
Yeah, right.
Okay, very interesting. All right, let me see. there are a few questions in the live chat, but we'll get into them shortly. So if we go back to this slide that you're talking about, the calculation of the gradients, I didn't quite understand. Sorry, that one. So here you were saying there are two different methods that you can use for calculation of gradient. One is like essentially finite difference, and one is the parameter shift. Can you just quickly recap this slide? Why are there two different methods, and what are the pros and cons of using each?
Mm-hmm. Yeah, so in the beginning, what people used for computing these derivatives were just finite differences. Yeah, I guess because it's a well-known technique to compute derivatives of arbitrary functions. And here, basically, the precision of your gradient is limited by this epsilon. So basically, you predefine this epsilon and then compute first the expectation value of your circuit with the parameters shifted by epsilon, then the expectation value of the unshifted circuit, and you divide this by epsilon, and you get an estimation of your gradient, which is fine. But it turns out that for quantum circuits, there's actually a relatively easy way to also compute the exact gradient, just by the way that these gates work. So we can also use the exact same circuit that we use to do our computation, but we once shift the parameters to plus pi half, compute the expectation value of this, and we take the difference with the same circuit, but where the parameters are now shifted by minus pi half, multiplied by a factor, and this is the exact gradient. And the downside here is that here we have to compute basically per parameter two expectation values, whereas for the finite differences, we only have to compute one expectation value for each parameter plus the unshifted version expectation value. But this is not an exact gradient.
Okay. So essentially, the first one is sort of a replication of how we do it in classical, and the parameter shift one is more specific to how the quantum circuits behave, and also gives the exact gradient.
Right.
Okay, very interesting. And R and S are parameters that we choose?
Yeah, so these depend on the gates that you use. But for the type of circuits that we use, R is always 1/2 and S is always pi half.
I see. So those are given parameters, essentially. Those are not like epsilon.
Yeah.
Okay, very cool. All right, so let's take a look at the live chat questions. A few people are asking for your contacts to follow up with you, and you had your slide, so we'll upload this slide, and folks can check that out. And I guess a question that we should expect is, when would quantum processors take over TPUs and GPUs, in your opinion, for commercial purposes?
Yeah, I think this is still a long time to go. So we could see some NISQ era things, I would say, in 5 to 10 years, but this is very like small scale applications. It's nothing that you can already use in a full-blown industrial context. For that, I think it will still be a couple of decades, and we would really need at least very good error correction, if not for current devices.
Okay, cool. So my last two questions. First one is, the first time I came across your work was on the TensorFlow blog. Was there any contribution from your work into TensorFlow Quantum, or was that just a generic blog there?
Yeah, actually, I was involved with Google and the University of Waterloo in developing the TFQ framework. So basically, I was kind of a guinea pig for the first version of the framework. And then also the Layerwise learning is also part of the TFQ white paper. So
very cool.
That's where that comes from.
Yeah. All right. And as the last question, what's next for this work or your line of research in general?
So what I'm currently working on is using quantum circuits for generative learning, because basically what a quantum state is also just a probability distribution. So I'm working on using this fact to do generative learning with quantum circuits and see if we can somehow gain an advantage by doing that with parameterized circuits.
Okay. And by generative learning, you mean like generative models, like for molecule generation purposes, for example, or do you have like a particular use case, or just generally, theoretically, is it possible?
Yeah, so for now, I'm just looking into generative learning in general, but like possible use cases. So I work in industry, I'm doing an industry PhD, and there, for example, generative learning can be used for anomaly detection and the like. So it's also interesting from that point of view.
Mm-hmm. All right, very cool. Awesome. I guess that's all the questions. So we can wrap up the session. Do you have any last words to share? Otherwise, we can wrap up.
Yeah, just I think my Twitter account was also shared. So if there's still some more questions, feel free to contact me. And thanks for having me today.
Sounds great. I guess there is a last question from live chat. Somebody's asking, what's the best way for an AI engineer to get their hands dirty with quantum research? Do you have any suggestions? Because I think you had a bit of that path as well, right? Like you worked as a machine learning person in industry and then entered quantum research. So what's your advice for everyone who wants to do that?
Yeah, I think a good first starting point is to look into the mathematics of quantum mechanics, not so much the physics, but first understand from a mathematical point of view what a qubit is. Basically, there's a lot of linear algebra, and you already know that as someone who's in machine learning. So I think that's a good first point. So you could, for example, if you really want to delve into the details, you could read the TensorFlow Quantum White Paper, which introduces a lot about how we train quantum neural networks.
Very cool, definitely. And I guess the Bible of quantum computing is the Michael Nielsen and Isaac Chang's.
Yeah. So if you really want a deep dive, then go ahead and
yeah,
read that one.
Definitely. Awesome. All right. Thank you so much, Andrea. Really appreciate that you spent the time with us today. I definitely learned a lot and enjoyed our conversation, and I'm sure our audience has as well. And hopefully we'll bring you back soon for more of your work. Thank you.
Thank you. Happy to join again.